Yesterday we talked about the physics and the mechanism of the friction stir welding. You have seen in the friction stir welding, for developing the joint, you need to first thermally soften the metal uh, using the heat generated, which comes from both the friction as well as deformation. So the friction is the primary contributor towards the heat generation, followed by the deformation, that is the secondary source. Once the metal is deformed softened, then there is a transport, or you can say a movement of the metal from one side to another, from front to back, and like say advancing side to the retreating side, and retreating side to the advancing side, like that. So that leads to so these are two things which are prerequisite uh, for developing the metallurgical continuity. Okay, so if you see here, we are having the deformation, and the magnitude of the deformation is very high. Actually, the strain may be 500 to 1000 also. Likewise, the temperature rise is also significant. Temperature rise, depending upon the metal, may go from say 300 to say for soft metals like magnesium, aluminum, maybe even 1000 degrees centigrade for steels, the high temperature metals. So most of the time this temperature is greater than the recrystallization temperature. So the peak temperature being generated during the friction welding is usually greater than the recrystallization temperature. So this is one aspect, and the second is the metal is deformed heavily, so that also facilitates the severe deformation of the metal during the welding, during the friction welding. This also and this severe deformation of metal during the welding, especially at a high temperature. You see, so the combination of the severe deformation at a high temperature, this leads to the a situation of a very dynamic recrystallization. Okay, and because of this dynamic recrystallization, we get extremely fine and equexed grain structure. So now this fine and equexed grain structure is developed. Now here we are not talking about the phase transformation. Here we are talking about the change in the morphology of the grains. So those metals, like say the precipitation hardenable metals, when they are heavily worked, refined, so at a high temperature all precipitates get dissolved. So you find the weld zone free from the precipitates. This is one thing. So weld zone which is being formed is free from precipitates basically. But if you talk likewise, the work hardenable metals, they are all earlier the dislocations will be lost, but you may find that due to the heavy deformation coupled with the rise in temperature, usually there is a work hardening. So that in turn increases the dislocation density and results in the improved hardness and strength of the weld zone. Then coming to the transformation hardening metals, this is altogether different thing. Like higher temperature leading to the austenitization, followed by the rapid cooling leading to the, like say, the pearlite and ferrite. These forms invariably martensite. So you get the increased hardness and strength of the weld zone. So the kind of the changes which are taking place in terms of the phases, in terms of the micro constituent, that is altogether a different thing. That will depend upon the type of metal which is being processed. But most of the time, with most of the metals, this dynamic recrystallization coupled with a fine grain equexed grain structure that is formed in the weld nugget. This is what happens with most of the metals. So what is important here is we have to see what are the peak temperatures which are being generated for a given set of the conditions, and how the deformation is being affected during the FSW. These two things probably will dictate the kind of the grain structure, microstructural aspects, and the mechanical properties accordingly. Okay, so now if we see any weld joint being formed by the friction stir welding, so typically friction stir welding will be leading to the development of weld nugget like this, okay, which is extremely refined and recrystallized zone. So we can call it as weld nugget zone or simply NZ, okay, simply NZ, nugget zone. But next to that there will be a very thin zone of few micrometers, like say maybe 2 micrometer, 4 micrometer. Next to that there will be a zone which is just strained, having the elongated or deformed grains in a particular direction, deformed grains in particular direction. So this zone adjacent to the nugget zone is being termed as thermo-mechanically affected zone. Now you see since this zone is extremely fine or thin, so you cannot see using the maybe optical microscopy or using the naked eye using stereoscopic microscopes, but you need high resolution as well as high magnification to see the TMAZ zone or thermomechanically affected zone. So in short, this is termed as TMAZ, and the weld nugget zone or nugget zone is termed as NZ. Okay, so this TMAZ zone, since it is very close to the weld nugget, so which is having the effect of both high temperature as well as the strain which is being experienced by the base metal or the metal adjacent to the weld nugget area. That is why it is called thermomechanically affected zone, having the strained or elongated grains. Okay, so as I said, so very refined and recrystallized grains in the nugget area you have. Thereafter you have the zone which is just affected by the heat or rise in temperature which has been there in the weld zone due to the frictional heat as well as the deformation heat which was generated. So as per the rise in temperature, as per the amount of heat which has been supplied, there can be different sizes of the heat affected zone. So there are few things. What are the factors that will be governing the size of these zones and what will be the properties of these zones? So because like let's say this is the joint, okay, this is the weld nugget area in simplified case. Next to that you have TMAZ, okay, next to that you have HAZ. So these are this is the HAZ, right, and in between you have TMAZ. So you apply a load, okay, so the base metal both the sides. Now where from the failure will occur, that will indicate which zone is weak. Failure can occur from the weld zone, failure can occur from the TMAZ zone of one side or other side, or it can occur from the HAZ, and that will indicate what is the area which is leading to the weakness or area which needs attention for improving the joint performance. Say the base metal strength is 250 MPa, and if the joint strength is coming 200 MPa, then you can simply calculate the joint efficiency from 200 divided by 250. That's simple thing. But to improve the joint efficiency, where you have to focus, that will depend upon the location of the fracture. It can be TMAZ, it can be HAZ, it can be TMAZ, or it can be your nugget zone itself. Okay, so there can be lot of hardening or softening of the different zones. What are these zones being affected by? So HAZ is directly being affected by the amount of heat that you are supplying. Net heat input that is being given. So based on your RPM and the welding speed or the traverse speed which is being used, the combination of these two, and for a given tool design, and like otherwise there will be like other aspects related with the tool, where is the shoulder diameter and the pin diameter. These two also will be affecting the way by which the net heat that will be generated. So for a given tool design, it is RPM and the welding speed. If the tool design is also one of the parameter which is being investigated, then you can have variety of tools, variety of pins. So the shoulder diameter or the pin diameter, and likewise their ratios as well. So in general, so all the factors which are increasing the heat input, like increasing the RPM or reducing the welding speed or traversing speed, okay, or increasing the shoulder diameter, increasing the pin diameter, or increasing the shoulder to the pin dia ratio. Okay, all these will be contributing towards the increasing heat input. Okay, so increasing heat input will simply be increasing the grain size of all the zones. Whether it is the weld zone, your grain coarsening will be taking place, or it is the HAZ zone. Both will be affected by this way. Not just HAZ grain size will be, but HAZ width will also be affected. You keep on increasing the heat input, you will notice that the width up to which the structure or properties are affected, that is also getting increased. So these are the different factors that we have to consider, and the way by which heat and the way by which the deformation of the metal is being affected due to the change of these parameters, that will indicate how the properties of a particular friction stir weld joint will be affected. Okay, so this is these are the different parameters about which we will be talking, and the way by which they will be affecting the, like say, the weld thermal cycle, you can say, that gives you idea of the heating rate 1, peak temperature 2, and the cooling rate 3. So the weld thermal cycle of weld zone or of the heat affected zone or TMAZ zone, all those can be of our interest, and that can be easily studied and investigated. Let's say what we do to study the weld thermal cycle, we will be installing the thermocouples like this at different locations, and then during the welding we'll be recording the variation in temperature as a function of time, say 1, 2, 3, 4. So you will be getting the temperature variation like this. Okay, so the different locations, the different kind of the weld thermal cycles that will be realized like this. So the point 1, point 2, and likewise increasing distance, reducing peak temperature, longer time it will be taking to reach the peak temperature, like that. So reducing the heating rate, reducing cooling rate, reducing peak temperature as a function of time with the increasing distance from the weld zone area. Okay, so those are the other aspects about that we'll be seeing. Thereafter, apart from this, the macro and microstructural aspects of the FSW joint, we'll be seeing how we can reduce the HZ zones or the adverse effects related with the high heat input. So in connection with that only, like stationary shoulder friction stir welding, this is one variant which has been developed, and thereafter we'll be seeing another variant, that is friction stir spot welding, which is used just like resistance is spot welding. This is also another variant which is used for developing the joint in lab joint configuration. And so technological aspects related with the friction stir spot welding, and the two typical methods which are used for developing the friction stir spot welding. About that we'll be talking. And lastly, I will be also talking about the friction surfacing. This is also interesting, where some kind of the deposition of the metal takes place just to modify the surface properties. Okay, so let me show you some of the things related with this, whatever I have said. So considering this background, I hope you will be able to get what I will. Yes. So this is what I have just said, like in a typical friction stir weld joint, you get the 4 different zones. Say base metal far away from the weld nugget area, which is not being affected by the heat or the deformation. The third zone, which is little closer to the weld nugget area, that is 1. This is the weld nugget area. Next to that we have TMZ zone, both the sides. Then we have the heat affected zone, and then at the end we have the far away the base metal. Okay, so the third zone here is the HAZ region, and the second zone here is the TMAZ zone, is the thermo-mechanically affected zone, and this is the weld nugget area, which is refined, recrystallized, and the fine grain, the weld nugget area. Okay. So this zone, as I said, the thermo-mechanically affected zone 2 will have the elongated, deformed, and strained grains. The heat affected zone will have the coarser grains. It will not have any effect of the strain or the deformation. This may be coarser. This may have a lot of other effects like the dissolution, reversion, or recovery, that will be leading to the, or even hardening also, or softening also. It depends upon the kind of metal system. Like in a steel, if it is simply annealed steel or normalized steel, it may get hardened. If it is Q&T steel, it may get softened due to the over tempering kind of thing. Okay, so this is one aspect of the friction stir weld joint. I have already explained using this whiteboard earlier. Now what you have to see, this is interesting one, this diagram. Let's say, how does the weld thermal cycle affect with the rotational speed and the translational speed or the welding speed. So say the first set of the parameters like 400, 700, 1500 or 1200, this indicates the rotational speed or RPM of the tool being used. Okay, so for a given tool design, for a given workpiece. Now the second parameter is indicating this 80 mm per minute kind of the welding speed or traversing speed. 200, okay, 1000 and say 120. All right, so the different RPMs and the different translational speeds. So the predominantly, if you will see, if you work with the lower RPM and the lower traverse speed, then what you are getting, lower RPM and lower traverse speed or welding speed is giving you the profile, this one. So the peak temperature is lower, it is taking longer time to reach the peak temperature, heating rate is lower, cooling rate is also lower. Okay, that is what you can see. If you work with the then B, curve B, you see rotational speed is little higher, so you are getting higher peak temperature, and your translational speed or welding speed is also higher, then the D1. So what you are getting, your heating rate is high and cooling rate is also high. Your and the peak temperature is also higher as compared to that of the 480 kind of parameter. Now when you work with the C, this is very interesting combination. When you are building RPM, rotational speed is maximum, say 1500, your peak temperature is here, but your welding speed is also very high, so heating rate is extremely high. Same is true for the cooling rate. Okay, so very high heating rate and very high cooling rates are observed when you work with very high RPM and very high translational speeds. It's just like high rate of the energy delivery, and just like a laser source, high power density heat source is being moved very fast. So that's what, in that case, the kind of the weld thermal cycle that we get is corresponding to the C. Okay, so here this C is interesting one, that although temperature is not as high as that corresponding to the 1200, but higher RPM coupled with a higher translational speed is leading to the very high heating rate followed by the cooling rates, high cooling rate. This is interesting actually, because this will be reducing the heat, net heat which is being delivered to the base metal. High RPM will facilitate the high rate of heat generation, but at the same time high translational speed will reduce the net heat being delivered, and that is why you are getting the high heating rate coupled with the high cooling rates. Okay, and if you see this D is interesting one, where higher RPM leading to the, let's say, but the travel speed is low, 120 only, so you are getting lower heating rate but a higher peak temperature and the lower cooling rates. Okay, so what we need to see is the combination of RPM and the welding speed or translational speed, that traverse speed, that will be dictating the kind of weld thermal cycle that will be experienced by the base metal or by the heat effector on a particular location. And it is the temperature and the time combination above which a particular metal is held. So if you see, if the temperature of interest above which a particular metal is held is in this band, say how long a metal is held above 150 or 200 degrees centigrade. So if 200 is the critical temperature above which if it is held, then this temperature is very short for welding parameter of 1500 and 1000 combination, welding 1500 RPM and 1000 mm per minute speed. So the high temperature retention period is extremely short. On the other hand, if you talk of like say 1200 and 120 combination, 120 of the traverse speed, then for this 200, the temperature, the time for which the 200 and above temperature is maintained is much longer. It's like 2 to 3 times longer time for which this is maintained, and this may be further longer for your the further lower speed and lower RPMs. That's what you can see here. Okay, for like say 400 RPM and traverse speed. So here it's good from the welding point of view, from net heat input point of view, to use the higher RPM coupled with the higher welding speeds, so that you can achieve higher temperature and you can and that too at the lower heat input, lower cooling rates. So that will be favorable actually from the welding point of view. Okay, so if you change the parameters, and that is why you see RPM ratio of the RPM and the welding speed can also give you the interesting aspects, like what kind of the things should be used. This is just a kind of now I'll be using the erase. Okay, so just to For your better understanding and appreciation, I am showing you the two examples of frictionist weld joint, say of aluminum alloy. This is an example of, like, say, aluminum copper alloy. So when the joint is made, you get a weld nugget area like this. Okay, in macroscopy, you cannot see the TMZ zone with the greater clarity, but it will be there. Okay. So weld nugget area looks to be fine, and this is side your HZ, both the sides. So if you see the microstructural aspects, the very refined equexed grains in the weld nugget area, and this TMZ zone, you can see the grains elongated and strained grains in the TMZ zone, while the grains are coarser in the heat affected zone. Okay, so these are the three microstructures of three different locations that you can see in the macroscope. Okay, the heat affected zone, weld nugget, and the TMZ zone. Okay, this is one thing. I have one more and a better example. Here you can see the things with a greater clarity. What you can see here, say this is the base metal in cast condition, as cast aluminum alloy. This is having all silicon and aluminum, iron, silicon needles, and eutectic silicon and aluminum. White grains are aluminum and eutectic silicon. These things, when they are deformed, you see, they get refined, they get fractured, and that's why you get all these things. But in ester zone, further finer grains you can see here. So the B is kind of the base metal, C is the TMZ zone, and your ester zone is D, corresponding to the ester zone. So very fine, homogeneously distributed, refined grains you can see here. But this is a silicon only, because this is aluminum silicon casting. Okay, so here you will not see, and the silicon has been refined significantly, and it is present in the matrix of the aluminum itself. So the cast structure here, eutectic silicon is present at the grain boundary. That is what you can see. Okay, now all those two were the butt joints developed by the frictionist welding, and this is the lap joint developed by the frictionist welding. Yesterday I was talking about this kind of thing only. This is the lower plate, this is the upper plate, and this is the interface. Okay, and here the tool would have been plunged like this, and the it would have been moved. Okay, so like this. Okay, this is the zone which has been affected. So this is the weld nugget area. If you see the interface zones, so wherever you will see this kind of the structure where weld nugget is leading to the interface, leading to the development of interface between the two base metals. If you see one base metal 1 and 2, the two are going to be getting connected through the structure like this. Okay, an interface of this kind. So these structures at the interface, these are called hooks. Hook length and hook height. You see, the length and the height, of course the orientation, whether it is perpendicular, inclined like this, inclined like this. So the hook length, hook height, and its orientation, these are the few things that affect the joint load carrying capacity, that is the tensile shear strength of the weld lap joint developed by the FSW. This is one thing. The second thing that I want to tell you, just like any FSW joint, here also you get the TMZ zone, HZ zone, because the bottom plate is not much affected by the FSW. The most of the effect or the stirring is being done in the top plate. Okay, so the TMZ you will be getting mostly in the top plate, and the TMZ extremely will be extremely narrow in the bottom plate, because it is not, so whatever is the effect is there of the bottom of the pin, and that will be leading to the minor development of the you can say TMZ. And likewise the heat affected zone will also be narrow, because at the top you have the very large dia shoulder which is developing lot of heat. So TMZ and HZ mostly will be developed in the top plate, and the TMZ and HZ in the bottom plate will be very limited. Okay, I hope this is an important aspect in the lap joining using the friction welding. Most of the stirring is happening at the top plate. Stirring happening in the bottom plate is extremely limited, and that is why you find the much wider HZ and much larger size of the TMZ as compared in the top plate as compared to the bottom plate. That's it. That's what I want to tell. Now this is an interesting one. What I have said so far, FSW joints, when you develop of the different metals, you find the different performances. Sometimes your the base metal is weak, sometimes your heat affected zone weak, sometimes even TMZ is weak, or even it can be the weld nugget also can be weak. So it depends. So here I will show you the two examples. These two examples are, like say this one corresponds to, the first one corresponds to that of the steel. So let's say your annealed or normalized steel, when subjected to the friction stir welding, rise in temperature is up to say 800-900 degrees centigrade, followed by the rapid cooling. So invariably it forms the martensitic structure in the steel weld joints, and that's why what you get, the base metal is fine, but here this is the base metal, this is the HZ zone, and this is the weld nugget zone. So HZ is harder, weld is further harder, weld nugget is further harder. So both the sides you are having the HZ like this, which is harder but not as hard as that of the weld nugget area, and then you have the base metal. Okay, so here what you are getting, you see the martensitic transformation and the work hardening effect both. In case of the HZ, you have primarily the combination of the martensite plus soft phases like pearlite and ferrite, because here martensitic transformation may not be perfect. And the same is true for both the zones, both the sides of the heat affected zone. Okay, so this is the story of the transformation hardenable metal, where your weld nugget and HZ are stronger and harder. They are becoming stronger and harder than that of the base metal. So certainly your failure is not going to happen from the weld and HZ zone. Failure will definitely occur from the base metal only. Okay, but the problem with this kind of hardening is what? The problem is this, that the weld and HZ is getting embrittled. Okay, so you may notice because of this kind of transformation, you have lost your entire the 150 joule the toughness. Now you are left with like say 10 joule or 20 joule only. So your the joint is not tough at all, and you may not use it for any functional or engineering application. So that's why efforts are always made to develop the FSW joints of such kind of the metals without much compromise on the toughness as well. Okay, so as towards that a few efforts have been made. Like in that case, during the steel welding, what we do, like say this is the weld line, this is the tool location. So before welding, what we do, using the flame heating or induction heating, first you put in the flame or coil, induction heating coil, before the tool is passed or workpiece is passed through the tool. So first do the preheating. So the preheating will be softening the metal, that's one, inducing the ductility, reducing the strength, yield strength, and facilitating the welding, that's one. Another is it will be reducing the cooling rate. So the tendency for the formation of hard and brittle martensitic transformation, that will be reduced, and as a result of that you will be getting the softer HZ and you will be getting the softer weld nugget area. So this is an example of hybrid FSW where some kind of the flame or induction heating is used. So that you can say those kind of variants you can term as a thermally assisted. Okay, thermally assisted FSW. So you use the external heat source. It may be in form of, even people use TIG arc also, although intention is not to melt the things much, maybe just to preheat, or flame can certainly be used. Induction heaters are used so that the things are heated to high temperature enough. Preheating is also limited. Actually, preheating is also not much. Maybe you need a preheat of 100 to 200 degrees centigrade. That's kind of a preheat that we need in normal steel welding, unless the hardenability is extremely high. Okay. So you see, the preheating or external heat assisted FSW, they can help in developing the reasonably tough joint, if not very tough joints, so that the embrittlement, extent of embrittlement is reduced. If you talk of the aluminum alloys, especially the precipitation and work hardening aluminum alloys, the story is quite different. It's completely different rather. So in the precipitation hardening category as alloys, or in work hardening category as alloys, the two different kind of the variations are observed. So the first one is the precipitation hardenable aluminum alloy, where you see the base metal is harder, it's fine, but as the heat affected zone is compromised, hardness of heat affected zone is compromised very badly, and you get the minimum hardness zone in the heat affected zone only. Okay, the weld zone is also softer because you have whatever precipitates you had, everything has lost. You don't have anything. The same is true for your, let's say. So what happens? Your immediately after welding, you see it is very poor. Hardness of the weld and HZ zone is very poor. But after 4 months, when some kind of the precipitate formation that is taking place, there will be marginal increase in the hardness. Okay. So in this case, immediately after the welding, if you perform tensile test, then you will notice that the failure will certainly occur from these weak zones. And that is the HZ. Because this is the minimum hardness zone, and failure is going to bound to take place from this place only. Okay. On the other hand, if you take another type of the aluminum alloy or any alloy which is showing the greater work hardening tendency, okay, in that case you will notice altogether a different kind of trend. What is that? Because of the work hardening and deformation, your weld nugget is harder and is stronger. Although HZ is softer and weaker, because your all probably recovery and recrystallization and grain growth has resulted in significant what you can call softening. But if the metal is showing natural aging significantly, the metals which show significant work hardening as well as the natural aging, then you will notice, okay, work hardened marginally, showing the little greater work hardness in the weld nugget area. HZ is softer because you have lost everything in the heat affected zone because of the, like say, the reversion or your the recovery or annihilation of the dislocations, etc., or grain growth. So your HZ is softer, it's fine. But on the other hand, if you see the weld nugget is harder, it's one, and after 4 months you will see significant precipitation hardening or natural aging is taking place. You may restore the hardness. So there is a typical aluminum alloy, aluminum, zinc, magnesium. So after the 7 days you may have a story like this, but after the 3 months you may have a story like this. So here, so the structures which are to be made of aluminum alloy after the welding, if they cannot be subjected to the post weld heating, then they need to be made of those kind of the aluminum alloys which can be naturally aged. So if something is happening or aging is happening or hardening is happening automatically, naturally, it's good. So aluminum, zinc, magnesium offers such kind of the behavior where it will get naturally aged. Maybe sometimes within month also it gives a lot of improvement in the joint properties. Immediately after the welding you would have lost everything, but the precipitates reprecipitation occurs during the naturalizing period, and that in turn leads to the restoration of the properties. That's very good side of certain aluminum alloys. So you see the kind of the strength or hardness distribution that you get in the FSW joints. This there can be a lot of varieties for steel, for only precipitation hardenable or precipitation hardenable and work hardenable metals. You get completely different kind of uh, the strength variation. Okay, so this is the same what I have just said. Like if you increase the rotational speed for a given welding speed, will increase the rate of heat generation, that in turn will increase the peak temperature, and increased rate of heat generation for given welding speed will be delivering more amount of heat, that in turn will be increasing the width of heat affected zone. Increasing the width, increasing the heat input due to the increased rotational speed for a given welding speed will be leading to the increased heat input, that will be increasing the grain size. And if and IMC formation will be taking place in especially in case of the metallurgically incompatible metals being joined. So this is not applicable for the similar metals, but for dissimilar metals that will be applicable. Likewise, for a given RPM, if RPM or tool rotational speed is fixed, then increasing traverse speed or the welding speed means earlier if you are moving at 80 mm per minute and now you are moving 1000 mm per minute, then this will of a particular location the peak temperature will be reducing, with the heat affected zone will be reducing, grain size will be reducing. Likewise, and this is primarily attributed to the reduced peak temperature, a reduced high temperature retention period, and a reduced heat input. Okay, so this is the another thing, like when you are working with the different shoulder diameters for a given rotational speed. So increasing rotational speed, what it will be for a given rotational speed, increasing the shoulder diameter will certainly be increasing the peak temperature because more frictional heat will be generated. Okay, and increasing the shoulder diameter to the pin diameter ratio, this with the increase of the traverse speed, the same thing will be true for here peak temperature. When your the shoulder diameter to the pin ratio is small, like say the pin is of the 4 and the shoulder diameter is 8, so the temperature rise will be very low. It may not be enough even to develop the weld joint also. So that is why we have to optimize what would be the kind of the shoulder diameter to the pin diameter ratio. It may be like say 2.5 to 3.5 or more as per the metal to be joined, the kind of heat that you need to generate for thermal softening of the metals for developing the sound weld joint. Okay, you know the normal load, the shoulder helps to press the metal down, which in turn you know during the welding there will be a lot of movement of the metals from advancing side to the retreating side, from the front side to the back side, and all these moving metals must be consolidated, and that consolidation is helped by the shoulder, and the shoulder must apply sufficient force so that this kind of forging and consolidation action can take place. So if the normal load is limited, okay, normal load is limited, then you will find the discontinuities are less. Discontinuities are more for the lower normal loads. Heat generation is also less. Heat generation will be increasing with the increasing normal load. So is true for the joint efficiency. So when your normal load is very low, you generate very less heat, which may not be enough for developing the sound weld joint. That's why you get the lower joint efficiencies. Okay, and on increasing the normal load, your heat generation is increased, you get enough softening, freedom from the discontinuities, you get the sufficient or peak joint efficiency. So there has to be an optimum normal load, because if the load is too much, then you will find the surface has got depression or the reduction in localized cross section along the weld joint, so you will be losing the joint strength in any case. So there is a need of an optimum normal load, that's one. And likewise the tool plunge depth, tool plunging must be sufficient. If the tool plunging is limited, then you will notice that from the bottom side there is a lack of penetration, there is no joint development. Likewise, increasing the plunge depth will be leading to the increased heat input also, and therefore your peak temperature will be increasing. So there is a need of an optimum the plunge depth also for through thickness. That's why for through thickness penetration it is about 0.2 to 0.5 mm less. The pin depth is kept so that pin depth is less than pin length is less than 0.2 to 0.5 mm as compared to that of thickness of the sheet which is to be joined in case of the butt welding using the FSW. Okay, so that was about the few parameters related with the friction stir welding. So now I'll show you the stage friction stir welding. What you have seen, like you have one tool, right? Tool is having shoulder and one pin. So all these are integral connected with each other. So whenever the tool rotates, the shoulder rotates, pin rotates, and this section of the shoulder comes in contact with the workpiece, and the entire surface area of the pin also comes in contact with the workpiece. So all this section helps in generating the frictional heat basically. Heat generation by the shoulder is significant, and that is why you get the weld nugget geometry like this. So this section of the weld corresponds to the pin, and this top surface, additional top surface which is experiencing the heat and deformation, this corresponds to the shoulder. Okay, so this extra heat generation at the top is causing much wider heat affected zone, and that in turn is weakening the joint significantly. So the idea here is to, like, say if we can do something on this front. So what is being done, like you make the shoulder like this, and then you make the pin. Pin is a moving part while shoulder is stationary. So this is just outer frame which is also acting as a shoulder. Only the pin is rotated. So the pin is rotated. This is the critical section because there is a relative movement between the shoulder and a pin. This is the pin, and when the pin is to be rotated, so there has to be gap. So the metal will tend to flow through this gap. So this kind of the ingressing or filling of the metal during the welding, that has to be prevented. That's why the design of the stationary shoulder is little critical. So in this case what we are having basically, your only the shoulder remains constant, only the pin is rotated. Only pin is rotated, shoulder remains stationary, shoulder doesn't rotate. Okay, so this pin is plunged into the gap between the into the workpiece which is to be joined. So this rotation of the pin will be generating the heat. All the heat generation is limited in this case, and therefore you will see you need to apply extra heavy pressure here. So normal load that is applied during the stationary shoulder welding FSW that is much higher than the conventional FSW, and the pin generates somewhat lesser heat, certainly because there is no heat generation from the shoulder. So to ensure that the metallurgical continuity, greater normal loads are needed. Okay, I'll show you the typical geometry of the stationary shoulder on which we have developed certain joints. Like say this is the structural part. This is just to facilitate whatever the metal is coming out that is broken down, and this is the stationary shoulder which is used to keep the metal pressing. Okay, and this is the tool. Okay, only the tool pin is rotated, and these are the like typical joints which were developed using the stationary shoulder FSW using the 2014 aluminum alloy. Okay. This is the work done by our one of the PhD students, Sunil Simar. So here, if you compare it with the conventional FSW joint, if you see, conventional FSW joints gives you lot of wide heat affected zone at the top. This is due to the shoulder heat generation. Okay. Thereafter, you get the very wide nugget zone like this. Then greater heat generation is leading to the wider heat affected zone like this. If you work with the stationary shoulder FSW, then we get that heat affected zone is almost absent or it is very thin. Okay, and the nugget zone size is also reduced. And so the undesirable effect of the heat input are basically reduced. This is the point that I want to make. And if your heat input is reduced and heat affected zone is reduced, then your grain size will be finer. Number one, your reversion and annihilation recovery, all those things will be reduced. And these effects were further substantiated through the microhardness study. Like say, when you work with the conventional FSW tool, you get the much wider heat affected zone where there is a huge drop in the hardness like this, right? So this the width where there is a drop in the hardness, you can consider as a part of the heat affected zone. Okay, and this is the nugget zone. Okay, this is the nugget, and if you talk of this is the nugget zone, if you see in case of the conventional FSW, which is also a little wider. If you talk of the stationary shoulder FSW, this shown by the black lines. So here FSW, the HZ is much narrow. You can see here, this is the zone where such kind of the drop is taking place. Okay, drop in the hardness is taking place over a narrow zone, which is suggesting that drop is sharper although, but it is narrow. It is occurring over a very narrow zone, and the minimum hardness is also higher, which means your joint will be stronger than the conventional FSW joint. Your hardness is a direct indicator of your joint strength, and that will also indicate where from fracture will be occurring. So obviously you can anticipate fracture in a conventional FSW joint can occur from these two locations.